Hello all, good evening to one and all. So this is Archana from Amrita Vishwa Vidyapeetham, and I work at the Amrita Center for International Programs as Alumni Engagement Coordinator. We have our alumnus here, Dr. Prasanth Venugopal, who is currently an assistant professor at University of Twente in the Electrical and Electronics Department, Engineering Department. And we also have Professor Sethu from our Amrita Center for Wireless Networks and Applications. I hope all of you will enjoy this webinar on safe, reliable, and contactless energy transfer. Thank you for joining us today. Professor Sethu, over to you.
Thank you, Archana. Welcome everybody. Webinar, I'm sure you will benefit a lot. Let me give you a brief introduction about the university and more specifically the center, the research center I belong to. So Amrita, as you know, is a multi-campus, multidisciplinary university. We have campuses in several places, spanning several states in India, Tamil Nadu, Karnataka, Kerala, Andhra coming up soon, and then up north, near Delhi, and so on. We have a medical school, we have arts and sciences in multiple places, we have like 5 management schools, we have engineering in multiple campuses, and so on. So that is the academic side. More interestingly, I would say, on the research front also, Amrita does a lot of things. There are dedicated research centers at Amrita. So I belong to one such research center. So the campus is known as Amrita Puri. This is in Kerala near Kollam. And the center I belong to is known as the Center for Wireless Networks and Applications. So as the name suggests, we do a lot of research, applied research, that has real significance and real impact on the society, the research that we do. So we do offer bachelor's programs, master's programs, PhD programs. At our center, we offer master's and PhD programs. 3 streams of master's programs we offer. One stream is known as Geoinformatics and Earth Observation. And then there is another program known as Wireless Networks and Applications. And there is also a third program known as Biomedical Instrumentation and Signal Processing. So biomedical instrumentation and signal processing, wireless networks and applications, and then geoinformatics and earth observation. In terms of eligibility, if you have a 4-year degree, whether it's a BTech or it's a BSc, MSc or MCA, BCA, MCA, all these combinations, you become eligible. Of course, certain streams may not be eligible, but things like, ECE, EEE, CSC, and then for each specific area, for example, in geoinformatics and earth observation, even with a civil engineering degree, you could still be eligible. IT, electronics and instrumentation, MCA, of course, MCA is eligible for all these courses. A lot of MSCs, especially for geo, if you have a reasonable amount of mathematics background, with an MSc degree you can apply. And with some MSc disciplines, you can also apply for BISP and WNA, that is wireless networks and applications. BISP stands for biomedical instrumentation and signal processing. So if you have specific questions about eligibility, do contact us and we can give you further details. We could even tell you with your background which courses, which programs you're eligible for, and so on. So going on to, I'll be brief. I'll talk a little bit more about what you get by going through these programs. So one important thing I want to mention is the integrated PhD program. So, when you do your MTech, somewhere towards the end of your MTech program, you could decide to convert that into an integrated PhD program. So when you do that, your PhD essentially gets accelerated. So basically, you get to do less coursework during your PhD because, you would have done a lot of the required coursework during your MTech itself, and you also get to continue your research in the same area in which you did your project in MTech. So that accelerates your research also in PhD. So potentially you could make it like a 2+3 kind of a program. In 3 additional years you could also get your PhD, and on top of that there are some very attractive scholarships that are available also for the MTech program, more so for the integrated MTech and PhD program. So again, details you could get if you are interested by contacting us. We also have something known as a Center for Sustainable Development. So again, as you know, sustainable development is one of the primary goals of the current today's world, because that's what we've been lacking. So the development has happened, but not in a sustainable fashion. So there is a lot of research required to kind of streamline the development, make it more sustainable. So that is where we focus in the center called the Center for Sustainable Development. And guess what? The director of our Center for Wireless Networks and Applications is also the director of the Center for Sustainable Development, Dr. Manisha. As a university and its parent organization, we have adopted more than 100 villages across the country in India. So a lot of these research can actually find applicability in these villages that we have adopted. So it's not something that we will be working on in thin air. The work that you do will have real practical implication, and you could actually do a deployment of practical implementation, and figure out whether it really works, what is the benefit, and so on, and then tweak it as needed. So the other dimension that I want to highlight is that in terms of the research opportunities, we work very closely with a lot of international educational institutions as well as research institutions, across the globe. Again, in Europe, in the US, Israel, Australia, Japan. So we have collaborations. We have signed several MOUs with multiple universities, and also with research organizations like the British Geological Society, the National Research Council of Italy. These are some of the research organizations across the world with whom we have memorandum of understanding to work together. And of course, in terms of universities, there are multiple. UPC Spain, we have VRI University. In the US, we work with several of the UCs. We work with the University of New Mexico, and so on. The list goes on. University of Tel Aviv in Israel, TU Delft in Netherlands, and it's a long list. As you can see, that's why we have a lot of our alumni also in these places. Prasanth is an example of that. Our students do get to do their dual degrees and student exchange kind of programs, and thereby they go to these foreign universities during the course of their program itself, and they get an opportunity to continue the same research with their respective guides at the international universities. So because of that, when you do your PhD, you typically have an international co-guide working with you, and in quite a few cases, even during your MTech program, when you do your MTech project, you do get to work with a co-guide from an international university. So that's a very nice feature that you benefit from. And even the courses that are taught, many of them are taught by faculty from other places, like even the industry abroad. We have people teaching from Qualcomm USA, NEC UK, and also the academic faculty in the international universities. They're all like adjunct professors at Amrita, so they get to teach you. They also visit, when they visit India, they visit the university, so you get to also interact with them in person. Now, the third dimension that I want to mention, before I move on, in terms of faculty, even the resident faculty at Amrita, there are quite a few of them that have had international experience. I could quote myself as an example. I joined Amrita 8 years ago. I joined the center, and before that, I spent a considerable amount of time in the United States. I was working there in the networking industry. So I bring that experience to the table when I teach courses at Amrita. Okay. And there are many such faculty that are resident now at Amrita. And not only that, even in India, we have like the retired Director General of Geological Survey of India, GSI. He is a faculty at Amrita. So we also have some of the Indian veterans, who had a good track record, a lot of experience working in different roles, and they get to impart knowledge as part of these programs. And the third aspect, or whatever, N+1 aspect, I want to kind of slightly touch upon is the kind of projects that we do. So like I mentioned before, the projects have a direct, humanitarian benefit. So that is kind of like the DNA of the entire Amrita actually, all the research, thanks to our Chancellor, who's a well-known humanitarian leader across the world. The research at Amrita is, ingrained with humanitarian service, being useful to the society. So that is like a fundamental goal of all the research that happens at Amrita. I'll give you a couple of examples of the projects that we have done at our center, the Center for Wireless Networks and Applications. We have installed a landslide monitoring system in 2 different places in India. The first one, which was installed about 10 years ago, and that's been giving us data continuously, helping us to, provide early warning for the landslides. The first one is in Munnar in Kerala, and about 3 years ago, we installed a slightly bigger system in Sikkim, in a place called, somewhere near Gangtok. I forgot the exact name of the place. So there again, on the hill slopes, on the foothills of the Himalayas, we have a landslide monitoring system consisting of several hundreds of sensors which have been buried underground, all the way up to a depth of about 30 meters at different levels, right? And then different types of sensors. So it's a whole wireless network, wireless sensor network that, again, pumps a lot of data, and we have our own decision support systems which actually process this data and enables us to provide early warnings for landslides. And based on that, people can be moved to safer places and so on. And then there's one project. There's another project we came up with about 5 years ago. We call it the Ocean Net. We call it Ocean Net because it provides very affordable internet connectivity to the fishermen, the marine fishermen. When they go fishing, one trip could take them like 5 days or even more sometimes. So they are like completely isolated from the land, and they don't have any affordable way of communication. They cannot use satellites. Satellites are too expensive. So we came up with a system. We have installed 5 base stations along the coast of Kerala. So now pretty much from Kochi to Thiruvananthapuram, we have provided coverage for internet connectivity for the marine fishermen. And then coming back to today's seminar or webinar, we do a lot of research in smart energy, smart grids, microgrids, and so on. So we have executed Indo-European projects in this area. We have worked with several universities in the Europe and so on. And water management, that's another area. Oceanography, coastal weather monitoring, because we have this ocean net, that enables projects like coastal weather monitoring, oceanography, and things like that, and so on. So and there are so many other projects. Other thing is coming to this biomedical instrumentation signal processing. We have developed several wearable devices to monitor the vitals of patients, so they can be used for post-operative care and even for preventive care and so on. So we as we have a hospital in Kochi, world-class, fully equipped hospital cum medical school, and there's another one coming up in near Delhi in Faridabad. So we get to work with these doctors and physicians, and whatever we develop, we actually get to field test them with with their patients, and so we get the feedback from that. So in that way, again, it's a very rich and varied experience, and if you get a chance, you can talk to any of our alumni, and they will give you a good feel for the kind of experience that you go through when you join our master's programs, which can and a lot of people have continued to convert that into their PhD program as well. So to conclude, we have 3 programs, master's programs: geoinformatics and earth observation, wireless networks and applications, and biomedical instrumentation and signal processing. So again, if you need more information, you are welcome to contact us. With that, I will stop and I'll hand over the stage to Prasanth to start his interesting webinar to all of you. Thank you.
Okay.
Over to Prasanth.
Yeah. Can you hear me? Can somebody raise can somebody hear me?
I can hear you.
Okay. So thank you so much, Professor Sedu. Thank you so much to all the organizers that actually invited me to deliver this webinar. And as was mentioned, I was an alumnus of Amrita Vishwa Vidyapeetham. And yeah, so the topic for today evening is safe, reliable, and contactless energy transfer, a post-COVID technological revolution. So as you can see in the picture below, you see that, the future will be electric, number one, and the future may also have charging of these electric cars, which are parked in a parking bay or which are even moving, for example, by means of contactless energy transfer. Now, it's a little bit of a play of words also, this title, because Corona, the COVID situation, has actually forced us to become contactless. So in the post-COVID world, I hope that we as human beings resume our social contacts while energy becomes contactless. So that was a bit of a pun in that title. So I've organized my presentation in a way where I would introduce concepts on wireless power transfer, deal a little bit about inductive power transfer, which is a specific form of wireless power transfer. I'll give some highlights about multi-coil IPT systems and multi-frequency IPT systems. So these are cutting-edge sort of developments that are happening in the world of inductive power transfer systems. I'll deal a little bit with wireless power transfer for drones and also tell you like what is going on in the industry, what has happened, and where do we foresee applications in the future. Okay. So maybe I'll introduce myself with few words. So already I mentioned that I did my bachelor's in electronics engineering from Amrita University in Coimbatore. So I was in the 2006-2010 batch. After finishing my bachelor's, I wanted to pursue my master's. So I did so in electrical power engineering in the Delft University of Technology in the Netherlands. So this was in 2010-12. That time I was quite fortunate because when I finished my bachelor's, I was looking out for scholarships, and this is especially for people that are finishing their bachelor's or who want to pursue a master's or a research program abroad. So one of your funding mechanisms can also be the J.N. Tata Endowment, which is based out of Mumbai. So it's a very old endowment that actually has a history of sending out scholars from India. From the 1890s, so I think it is a partial scholarship and a loan-based scholarship. So it's an interest-free loan. So it's one of the funding mechanisms that you could see yourself getting. So I would encourage you to apply for that if you're looking out for positions. My MSc thesis was on wireless power transfer. So I started researching on wireless power transfer from 2011, basically. After completing my master's, I was offered a PhD position in the Delft University as well. My advisors were Professor Paul Bauer, who is currently the chair of power electronics in the Delft University, and my other promoter was Professor Bram Ferreira. Again, I was fortunate that both my research theses were awarded. So I got a University Fonds Delft Kofeli Energy Efficiency Prize for my master's. And last year I was awarded one of the 3 best PhD thesis prizes. So it was awarded by IEEE IAS. It's a worldwide prize. I was awarded in Baltimore in the United States. So after completing my PhD research work in 2016, I decided to join Qualcomm. So Qualcomm had an advanced R&D division called Halo, which was actually doing wireless charging. I'll describe a lot more about Halo a bit later, but it was by far one of the biggest players in EV IPT systems. So it was quite natural for me to join there. So I shifted out of the Netherlands and went to Germany for that. I followed it up with a year and a half or so with TDK Europe Gmbh. So TDK is a Japanese multinational corporation that actually manufactures passive components like ferrites and inductors, capacitors, as well as sensors, and also develops systems and so on. So it's a big multinational from Japan. They acquired a part of Siemens, which was called as EPCOS, and it got integrated into the TDK family, and I was working in the German division there. In June, I was offered a position to start at University of Twente, which is where I am currently. So I'm an assistant professor in the Power Electronics and EMC group in the University of Twente in the Netherlands. Yeah, so this is briefly about me. But it's also good to tell you a bit of the history of U Twente and the work that we do. So the University of Twente had a program for telecommunications engineering, and electromagnetic compatibility is a specialization within that field. So it was headed by Professor Dr. Frank Lefrink. Professor Frank is also a technical authority of Thales, which is a very big industry that actually manages a lot of EMC labs. So under him, there are 15 labs with 100 engineers. So he works part-time at the University of Twente. From I think August of last year, my professor and promoter, Professor Bram Ferreira, he decided to join University of Twente to create a program on power electronics, because there was no program on power engineering so far at University of Twente. These two disciplines somehow merge together right now. So the power electronics and EMC together is now the new group, and I've joined this new group hoping that we create a new lab which actually combines the strengths of these two worlds. So of course, both these professors are fellows of IEEE, and the EMC program at Twente was very well established, and Professor Bram Ferreira was also the past president of the Power Electronics Society. So the ambition of the group is actually to look at future power electronic systems that work at much higher frequencies, and where we can tame the problems that electromagnetic compatibility, the ringing and so on introduces, you know. So that's the vision of the group. Now I think I'll head into my topic, which is wireless power transfer. So what does wireless power transfer essentially mean? So wireless power transfer means, okay, you want to transport energy between two circuits without any wired interconnects between them. Now wireless power transfer can be achieved using multiple modes. So when you use magnetic fields, the type of wireless power transfer is called inductive power transfer. And inductive power transfer is by far the most mature and the most popular form of wireless power transfer. So we are seeing applications ranging from kilohertz all the way to megahertz. One also sees that the power level is from something as small as microwatts to hundreds of kilowatts, and efficiencies on a day-to-day or a month-to-month basis are being pushed higher and higher. So we are seeing probably 94, 95% efficiency, even at higher powers like 11 kilowatt and so on, you know. Of course, there are other modes of transporting energy. You can think of the dual of magnetic fields, which is electric fields. And in that case, that kind of power transfer is called capacitive power transfer. This field is not as mature as inductive. Of course, research is still ongoing. So that's why you don't see the flurry of applications or the flurry of power levels that you might expect with IPT and CPT, for example. But nevertheless, there is some work in capacitive power transfer as well. You can also imagine transporting power in the form of microwaves, in the form of light, that is laser, or even in the form of sound. So these are largely experimental. To give you a specific example, microwaves, the dream of NASA was once to beam, like, you know, solar energy from the sun onto Earth using microwaves, you know, but it's still quite an experimental technology. And therefore, we will focus the rest of our presentation onto inductive power transfer systems. Okay, so how does the totality of a system look like, you know? So inductive power transfer system has electronics. So we have power electronics, inverter that feeds AC onto like two pads, one placed on the floor. So this is called the ground or the base pad, for example. Another pad which is placed below the chassis of the car. And by means of this gap, we want to transfer power or energy, you know. So this is essentially how, let's say, a laboratory scale wireless power transfer demonstrator might look like, you know. But if you're looking at an industrial system, what are the blocks that constitute such a wireless power or a IPT system, for example? So we have energy that is coming out of our AC mains. So we can have a single phase AC or a 3-phase AC. So for example, in India, we are talking of 230 volts, 50 hertz systems for single phase. We rectify the AC 50 hertz component to make a DC power here. So we get a DC link. This link is typically less than 230 volts, so somewhere around 200 volt. But just like any power system, if you want to transfer energy, you probably want to do it at higher voltages. So one of the first system that you will encounter is a boost converter. So you probably want to change this 200 volt into something like 600 to 800 volt, something much higher voltage, so that you can transport power with much less currents, for example. Then the next and an important part of the system is the inverter. So we need to change this DC into AC, but AC of a different frequency, not 50 hertz, but we are talking of higher frequencies like 85 kilohertz. Why 85 kilohertz? Because standards regulate applications for different electromagnetic purposes, So when you want to do wireless charging for electric vehicles specifically, the standard dictates a small range of frequencies between 80 to 90 kilohertz, with 85 as the center frequency. So 85 kilohertz is what is mandated by the standard for wireless charging for EV applications, If we impose this 85 kilohertz directly into the base pad, because the base pad and the vehicle pad are separated by such a large air gap, to magnetic fields, air gap introduces large reluctance, which is essentially a lot of loss. And therefore, what happens is we hardly couple any voltage, and therefore we transport very little amount of power at much less efficiency as well. So we need to make tricks so as to make sure that we can transport power at required or appropriate levels, as well as at high efficiency. So for doing that, we do what is called as double tuning. So we tune the base pad, the inductance that constitutes the base pad, by means of capacitors. We tune it to the 85 kilohertz resonant frequency. So that is the first resonance. The same thing we repeat onto the vehicle pad as well, so that the vehicle pad is also compensated. So we perform reactive power compensation at the vehicle pad as well, and we tune it to 85 kilohertz. So we have a single tune and a double tune. So altogether, two resonances that are happening, one at the primary side and the other at the secondary side. By means of this, we are able to transfer power at good efficiencies and reasonable amounts of power as we design the system for. Then the next step is really to put it through the drivetrain or put it into the battery of our system. So you need to, because battery works at DC, you need to rectify it. And batteries, for example, for electric vehicles are at 400 volt. So you need to step up or step down the voltage appropriately. So in this case, step down. So you have a buck converter, which then conditions the power to what is necessary for the battery. So this, in effect, is how an industrial IPT system will look like, including all the components. What you see on the right is basically one of our first demonstrators. So this happened in the year 2011-12 when I was still a master student, and my senior master student was working on a project where we wanted to demonstrate wireless power transfer, but to a toy car. So as you can see, this is a toy car with energy storage in the form of supercapacitors, because in the year 2010-11, lithium-ion battery packs were not as accessible, So we were looking at supercapacitors as energy storage. So that's what you see with these 10 supercapacitor bank that you can see there. So I was working on building the system for the master thesis. Eventually what happened is, because the system worked with rather good efficiency, we decided to make this a part of our BSc program. So the BSc program in TU Delft has one of its objectives as a group work, where groups of students actually get to play with this toy, and they have to design the coils, and they have to design the capacitors, the resonant capacitors, while we actually give them the footprint for the inverter. We give them, whatever the other system requirements are. So by means of this, the students actually get to do a project that actually fulfills their requirement for semiconductor physics, for power electronics, and also fulfills the requirement for communication engineering, because one part of the module is also to develop a wireless communication system which actually can move the robo wirelessly, you know, or move this this toy car wirelessly. So yeah. Okay, so I was mentioning that, you know, this large air gap transformer, as we call it, is one of the fundamental parts of wireless power transfer system. So this belongs to a regime of magnetic system which is called loosely coupled magnetic system. So what is loosely coupled magnetic system? So if you look at, for example, well-designed transformers that you're using in power electronic converters, or if you're looking at transformers that are present in the backyards, for example, they are characterized by a continuous and highly permeable medium, you know, whether it be ferrites or whether it be steel, for example. So you have a continuous and highly permeable media. So what does that imply? That implies that the coupling coefficient or coupling ratio of these two coils is very high. Typically, we are talking of 0.98 to 0.99 or even very close to 1 for that matter. So those kinds of magnetic systems belong to the regime of tightly coupled magnetic systems. But when we have such a big air gap, which introduce such a huge reluctance, we actually can't couple all the magnetic field that is produced from the primary onto the secondary. In fact, we don't even couple half of it, you know. So for all those cases where we are looking at coupling less than 0.5, this is called loosely coupled magnetic systems. To take specifically electric vehicles or vehicles for that matter, the clearance of a car typically is 10 to 15 centimeters. And that's large enough to make sure that your coupling is going to be quite small. So we are talking of maybe 0.1 or even less, you know, sometimes. Of course, when you have a coupled magnetic system, we can actually transport electromagnetic fields, or we can also transport electromagnetic waves. So when the frequency is very high, we are talking of waves. When the frequency is intermediate, we are talking of fields. So when we want to transport energy, we actually are talking of near field electromagnetic coupling. So we are talking of near field and not the far field, not radiative. So another distinguishing feature is the same inductor would be called as an antenna when you're thinking of waves. You know, but we are not talking of waves. We are still in the near field electromagnetic, let's say, induction problem. You know, so with this background, let's look at power transfer. So how does a coupled circuit look like, first of all? So when you have two inductors that are separated in air by an air gap, part of the magnetic field that is produced by the primary links with the secondary, and that part is called the mutual inductance. But there is a lot of magnetic fields that permeate each of either the primary or the secondary that actually doesn't couple to the other coil at all, and that constitutes the leakage. Okay, so this is a T network, as we call it. So this T network nicely characterizes a coupled system, but of course every coil has some resistance to it. So when you apply an AC field to a coil, you also have to transgress through the resistance of the coil. So of course a complete diagram will also have the resistance, and you connect of course the load across your secondary. One important feature to note is when we look at transformers, for example, and when we look at numbers, 11 kVA transformers. So the volt ampere rating of the transformer is conserved from both the primary as well as the secondary. So this is a direct corollary of Faraday's law and Ampere's law when you write it down. But the problem is when you're looking at loosely coupled systems where the coupling is so small, where you hardly induce any voltage onto a secondary, you can't denote a volt ampere rating to such kind of systems because you're hardly coupling power to the secondary, you know, so you cannot say the volt ampere in the primary would be equal to that of the secondary. So how do you quantify power in such kind of systems? So for doing this, we come up with a trick, and that trick is we look at two extreme operating modes of this coupled system. So the two extreme modes are open circuited mode of operation, which essentially means that this RL, the load resistance, is infinity. And when the load resistance is infinity, when it is open circuited here, all the current flows through the primary loop, right? So whatever is the voltage that appears across the mutual inductance is the voltage across the secondary. So the open circuit voltage is then very simply derived as j omega m I1. Now the next operating condition, or the other extreme operating envelope of such a system is the short circuited case. So short circuited case is where the RL is 0. So you essentially have a short circuit here, which implies that there's no current flowing through the mutual inductance at all, and all the current is flowing in this loop. So with that, you can easily derive what is a short circuit current. So you know what is the open circuit voltage, you know what is the short circuit current. These are two extreme operating modes. So now to dictate a power transfer to such a pad, what kind of power do we receive in the secondary? We can actually take a product and say that this is the maximum amount of power that such a system can drive. It may not be normally realizable, but this is the maximum that it can drive. So that's one way to quantify power in such kind of systems. But of course, in real life, wireless charging systems don't just have coupled coils, they also have a reactive power compensated capacitor, so you have capacitors which are tuned at both the primary as well as secondary. Now, when we are looking at power at the secondary, what happens to a resonant tank on tuning? So essentially what happens is whenever there is a resonance struck between an inductor and capacitor, either the voltage or the current gets scaled by the quality factor. And this is something that is very typical behavior of a resonant tank. So whether it be series resonance or parallel resonance, either your voltage or your current gets scaled by the quality factor. So what therefore varies between an uncompensated air-cooled coil to a compensated network is this additional factor, which is the loaded quality factor. So normally coils are denoted by a native quality factor, which is basically the reactance over the resistance of the coil in itself. But now we have a load in the system as well. So when you introduce the load as well, that is called the loaded quality factor. So it's omega L over R2 plus RL. So this is the scaling factor by which your power. So now you get a feeling of what happens really when you compensate the system. Your power gets an additional factor, which is this loaded quality factor, which therefore essentially means that you transport much more power than if you had a non-compensated or an uncompensated system, right? Good. What are the materials or what are the things that constitute a charge pad? Because the charge pad is basically a complex combination of different materials, each of which have specific electric and magnetic properties which are tuned for doing wireless power transfer. So of course you need copper conductors, as you can see here. So this copper conductor, when we talk of electric vehicle applications for 85 kilohertz, we are talking of Litz wire. So Litz wire is a type of stranded copper wire. The reason is because as frequency gets pushed higher, you introduce like high frequency effects like eddy currents, like skin effect, proximity effect, and so on. So, so therefore the losses in a solid copper wire is going to be very high when used at much higher frequency. So we look at stranded wires. We also need materials that can shape the magnetic fields, so ferrites are materials with very high magnetic permeability. So the idea is like, the magnetic field then easily passes through the ferrite so that it can pop onto the top where you want to send the power to. So you have nicely shaped the magnetic field using the ferrite bars. A problem with normal, let's say, couplers is the fact that you have bidirectional flux. So when you look at a simple coil, you have flux that is penetrating above the surface of the coil in the plus Z direction, but you also have flux that is penetrating below the minus Z direction, So you actually have a fountain flux, as we call it in our nomenclature. So the fountain is going upwards and the fountain returns below the ground as well. So we don't want like the magnetic field to go below the plane of the coil, So we introduce shielding mechanisms. So one of the shielding material is, for example, aluminium, which is a metal. So when metal is exposed to changing or alternating magnetic fields, what happens is it induces currents onto the metal, which is called as eddy currents. Now, this eddy currents create heat, it creates losses, but it has an important feature. Because it obeys Faraday-Lenz's law, the magnetic field is produced in a direction that it opposes the cause that produced it. That essentially means that the magnetic field of the eddy current will be in direct opposition to the magnetic field produced by the coil in itself, and therefore nothing can penetrate, no magnetic field can penetrate below the plane of the aluminium shield, So all these materials have properties which have been designed in such a way that we enhance power flow to the vehicle. When I started my research, we were looking at single coils. So as you can imagine, you could have circular shaped coils, rectangular shaped coils, square shaped coils with ferrites and with aluminium shield and so on. It was also the time where multi-coils, so as you can see, segmented coils, so you have multiple single coils coming in or were being researched. Now, the question that we began asking in Delft is like, why would I choose a certain coil topology over the other? So that basically means we had to look at a framework by which we understand the advantages, the disadvantages, and the peculiarities of each of these couplers in itself, So one of my first tasks was actually to come up with a sort of analytical framework by which we can understand how each of these coils or couplers behave. So for doing that, I would like to take a step back and understand the mathematics or the physics of such problems, So how do you quantify inductances and coupling? So that's the first step to understand before you solve such problems, So inductances are in general, especially for low frequencies, are in general a function of the geometry. So, for example, if you have more number of turns, the self-inductance increases. That's simply because the perimeter is also adding up and more turns enhances it further. On the other hand, the concept of mutual inductance, it depends on overlapping area. So that means that if you have two coils which are well aligned, perfectly aligned, the centers are perfectly aligned to each other, you would expect that they would have the best mutual inductance simply because the overlapping area of the two coils is a maximum. So all these generalizations can be understood mathematically. So one of the methods is to understand Naumann's integral, which is one very fundamental and powerful mathematical tool to understand inductances. So if you have some understanding of contour integration and everything, you can come up with a solution to this integral. Only thing to talk about is when you have mutual inductances, the two contours that you see for the integrals are the contours along the wires that constitute the pad. But of course, when you have self-inductance, there's no second coil, isn't it? So therefore, the two contours for self-inductance in that case would mean a contour along the center of the coil and one along the edge, So you have the same coil, one along the middle of the coil, and the other contour is along the edge of the coil. Okay. So I extended that theory further because the thing is, how do you describe multi-coil systems? So if you understand that magnetics is linear, for example, when you're talking of wireless power transfer coils, you have a very large air gap, and air core coils are linear. So they don't have non-linearities like saturation and so on, and you of course will not apply a DC to a coil, which can actually saturate the coil. So that's not happening either. So what you can do is you can actually apply when you are talking of multi-coil structures, like if you have n number of primary coils and m number of secondary coils, you can actually decompose by the principle of linearity using the principle of superposition. You can compose this into a single coil primary, a single coil secondary structure with all the parameters, the resistances, the mutual inductances, the leakages, and all that as being like summations, as being as obeying the principles of superposition. So by that, the power of this is therefore that if you understand how to compute a single circular or single rectangular coil, now you can extend the theory to a matrix of coils as well, and you can derive useful results. So, which is what I did, for example, and I would like to spend some moments to explain this curve to you. So let's say that you want to compare different coils or different couplers, circular, rectangular, square, segmented shapes, and so on. Using the analytical framework that I developed, I ended up calculating coupling as a function of misalignment. So what does misalignment mean? So when you have perfect alignment of the two coils, and if you move your secondary with respect to the primary along the x-axis, for example, circular coupler. What is the feature of circular coupler? So what you notice is, for example, at the best aligned point, the circular coupler has the highest coupling possible of all the shapes. Why is that? So if you investigate or if you try to understand a bit, circle has this beautiful property that circle has the highest surface area for a given perimeter of all the closed shapes. And like I mentioned to you, if you have two circular couplers now perfectly in alignment, and if they're very well overlapped, and if the shape in itself produces very high amount of area for a given perimeter, that means more mutual inductance for very little self-inductance, you will get the highest coupling. So for all the shapes possible, circular has the highest coupling at the best aligned point, which essentially means if you're looking at applications of wireless power transfer where you don't have movement, where you have a fixed secondary lying directly on top of the primary, go for the circular shape. You will use less copper, you will get much higher coupling and so on. But on the other hand, we are looking at electric vehicles, and electric vehicles are highly prone to misalignment. You know, you can never park your car at exactly the sweet spot that you want. So then when you look at other shapes, for example, rectangular and square, they don't exactly have the highest coupling at the best aligned point. But when you move laterally, what happens is, or what you notice significantly is that the decay that you see in the coupling, which you see for circular pads, which is really very drastic. So if you move even slightly your circular pad, you will lose quite a lot of power. But on the other hand, when you're talking of rectangular and square shapes, you have a much larger bandwidth, if you want, for coupling versus misalignment studies, you know. So therefore, they have much more tolerance to misalignment, even though you don't get the highest power at the. But if you designed it for this intermediate coupling value, which actually gives you the right power that you need, this is a feature that that is interesting for EV studies, you know, the tolerance to misalignment. Now let's take it a step further. What if I have a matrix coil, a DD coil? You have two rectangular coils placed next to each other, you know. So in that case, you actually come up with two peaks. So if you follow the diamond blue, you have a major peak, which is when both the coils of the primary are aligned to both the coils of the secondary, right? But now if you move it a bit towards the left or to the right, what you essentially see is you will actually have another peak, but it's not as high as the main peak, you know. So we call this as the minor peak. So you introduce a major peak, a minor peak, another minor peak, you know, because you can move left or right. So essentially meaning that if you misalign it, at least one of your coils in the secondary is getting power from one of your coils from the primary, you know. So you can extend the range of your power transfer, and that is also very important for us, you know. So the range of single coils is highly not enough for EV studies, and therefore we look at segmented or DD coil. Okay, so let's look at, so this is the reason why we chose DD coupler for EV studies. That's what I wanted to justify. Now, if you look at what is the magnetics of a DD, so you see these two red coils that you can see here. These two red coils are imposed by currents, but with a feature. The feature is that if you apply a clockwise current to this coil, you apply a counterclockwise current to this coil. So what happens when you bring in a directionality or two directions to the currents in the two coils? It essentially means that you have created for every half cycle a horizontal bar magnet, you know. So the bar magnet would assume a north pole at so this current would create, let's say, a north pole in the positive half cycle. Here it's a south pole, you know, so your flux literally jumps from the north to the south. You can see this in the finite element simulation as well, you know. So you have one coil, another coil, and you see this warping flux, as we call it. So the flux actually warps from one coil to the other in the circular manner. Now, if you have the same pad at the other side, so if you create a north pole for the half cycle, here a south pole is automatically created and a north pole, and you will see that the warping continues further, you know, that, so you get this kind of a flux concentration in such pads, you know. So this is the feature of the DD coil. Now, echo coils have a problem that if you want, let's say, to transfer power, and let's put numbers to it. Let's say I want to transfer 2 kilowatt of power by means of echo coil couple. You don't have one solution for transporting 2 kilowatt. You will come up with a flurry of solutions, because you can have a very big primary pad and a small secondary pad. You can have a very big secondary pad and a small primary pad. You may have 5 turns in one pad. You can also do the same thing with 15 turns, you know. So we have a lot of parameters that are possible for all our magnetics. But at the same time, I want to pick a certain suitable or sensible solution. So how do I do that? So then this falls under a regime of problems which is called as multi-objective optimization. So we look at multiple objectives. So let's say for wireless charging problem, you can have objectives like, okay, I want to transfer power with very high efficiency. So that's one of my objectives. Another objective can be that I want to minimize the area of my pad. You know, I don't want a very big pad in my vehicle because no OEM wants to put a heavy or a big pad in the vehicle. You know, so I want to maximize the area power density. Power density is basically power over area. Area power density is power over area, which essentially means I must make it make the area as small as possible. Another thing is also like, why should I have a heavy system which can do the same purpose? I want as low a weight as possible. You know, so these are the targets. But of course, all materials have constraints. So it's also, you don't want to push more than what you can through these materials. So for example, copper wire, which is transferring, the Litz wire, which is transferring 85 kilohertz of frequency, it has current density limitation. So when you're looking at 50 hertz, for example, copper wire, you can say that I can transport 6 ampere per millimeter square without any cooling requirements. But on the other hand, when you push the frequency higher, we have much more losses because of high frequency AC effects like skin effect, proximity effect, and so on. So then the current density becomes proportionally small. So we are looking at something like 4 to 5 ampere per millimeter square. You know, so I've written it as 25 amperes, but in reality, that's simply because I already chose the Litz wire. You know, so in terms of current density, it's something like 4.5 maybe ampere per millimeter square at 85 kilohertz. Also, for example, ferrites. Ferrites can't carry infinite magnetic field through itself. You know, they undergo saturation. So you need to be aware of that, and you need to put a constraint on that as well. You know, so for example, this material 3C90, it's a ferrox cube material. It has a saturation flux density of 0.45 Tesla, but hey, it's for room temperature. It's for lower temperature. But now, because we are transporting power, and if you're designing systems for 11 kilowatt or so on, then you better derate this as well. You know, you derate it to maybe 0.2 Tesla, you know, 200 millitesla, for example, because at high temperatures, the ferrites are even poorer when it comes to saturation. You know, another constraint is, for example, there are active limits that are being proposed by international bodies, including ICNIRP, which is the International Commission for Non-Ionization Radiation Protection, because you don't want to have a lot of radiating magnetic fields around your charge pad because of health reasons, you know, so you have limits for safety. So you need to abide by that. So you also need a constraint for that. Yes, so we talked about what are our objectives, we talked about what are our constraints from the materials point of view, but now what all can I change in my system? What are my solutions, for example, you know? So if you look at, for example, a pad, it has the Litz wire coils, it has ferrites, it has aluminium shield, each of which have like parameters, the lengths, the widths, the thicknesses. So each of them can be optimized. You know, so to give a specific example, number of turns, I said that, okay, we can change the turns from 15 to 40 in my coupler, which was for 2 kilowatt wireless charging system, you know, but why 15, why 40? These are limits based on like how big can your pad be? I don't want to go more than this, you know, so based on that, you propose the envelopes for your objective, multi-objective optimization. Okay, I can live with this much minimum, I can live with this much maximum, but nothing more. You know, so your solution space is restricted to this. The same thing is true for all the parameters that I just mentioned, the widths and the thicknesses. So we put parameters to all of them. So if you take, for example, N is 15, width is 10, thickness is 5, this represents one charge pad couple, right? So we are looking at one solution to the problem with that, you know, and then you do the optimization. But before you start optimization, a very good idea is to validate your model. So what does validation mean? Make a very simple simulation in a finite element tool. For example, I use COMSOL. You could be using ANSYS. You could be using any other tool for that matter. Make a very simple simulation of the geometry that you chose, with the idea that the parameters that you're getting out of your simulation can now be checked in reality. Because for building a very small coupler, you don't lose a lot of copper or whatsoever. And when you make measurements to measure inductances and coupling, you can make a correlation between what you see from the finite element tool to what is actually the reality, and that will give you confidence to then look at much more complicated, let's say, simulations, so you must develop this kind of confidence. And we did that in the lab. So we varied the course and we made, let's say, measurements and simulations, and to the degree of acceptable inaccuracy that we see in magnetic simulations, I think we were quite good. So even up to 5 to 10% is quite normal that you will see, and it's acceptable. Then you go ahead with making your more complicated models. The reason why I insist on this is because COMSOL, or for that matter, any finite element tool, is a very good tool that gives you all the colors that you can imagine, but they need not be the reality, so you should be careful if you're simulating something that's real. Okay. And the last step is to make some trade-offs. So what do trade-offs mean, or what do I mean by that? So as you imagine, all the variables can now play with a large range. So we are looking at a solution space that is big. So you're iterating between a lot of combinations. Can we do something to shrink that solution space a little bit? That's where trade-off studies help. So one of the trade-off studies is, for example, intra-core air gap. So in my coupler, we have ferrites not as a big block, but we have these not as a big tile, rather, we have these blocks, for example, these I-shaped blocks. So we do have air gaps between these blocks. Now the question is, we use coupling as a target. What we realized is, even if we leave, for example, 20% air gap between both the primary and the secondary, the coupling has already reached a maximum. That basically means I don't need to simulate from 0 to 20%, because it doesn't add any value. I can have up to 20% air gap, and yet my coupling has already reached a maxima. So why should I look at this set of particles? I don't need to, So the same thing we could do for another trade-off, which is, for example, the length of the ferrite. So this picture is quite interesting, So I show that the ferrite is much longer relative to the length of the coil, But in reality, the trade-off study showed us that, okay, even if you have 80% of the length of the coil that is being covered by the ferrite, you already hit maximum coupling. So why do you want to have a ferrite that's even longer? You don't need those solutions, So the ferrite lengths are therefore tied somehow to the lengths of my coil up to 80%. And if I've hit maxima, I'm not even bothered of it being even larger, So with all these and running the optimization, so I used particle swarm optimization because we had a history of doing that at TU Delft. So all those variables, all those charge pads then were compared for the objectives that we had. So the objectives were efficiency, area related power density, weight, and so on. So between those objectives, if you plot, let's say, the solutions, you will get a nice Pareto front. So Pareto is basically the optimal set of solutions. Because it's a multi-objective optimization, you don't have one optimum, you have several optimums. Now the question then is for the designer. So the designer can choose, let's say that if I say that, okay, I want to only look at designs where I get very high efficiency, but my important criteria is it should be less than 3.5 kilograms, So then I'm looking at some of these points. Further, if I say I only need solutions where my efficiency is above 85%, so it's 85% here and 3.5. So I look at 4 or 5 particle, and then I can probably give a weight to power transfer efficiency being more important, for example, than the weight of the system in itself. By doing that, I can select one of the particles. So that's how you refine your set of this optimal set of solutions into one particle that you build. And I did that. We transported power. So as you can see, this is the oscilloscope picture of the inverter that drives a square wave voltage. We use magnitude cancellation. I'm showing 180-degree phase shift, but we can also have other forms of magnitude cancellation square waveforms here. So it's called a quasi-square, in fact. And this is the two currents that you see in the primary tank and the secondary tank as well. So they are nice and sinusoidal. So that's what resonance does, resonance forces a sinusoidal current through the coils. These were the computed and the experimental efficiencies. So for 2 kilowatt charging, we were sitting very close to 92% efficiency. At the same time, I can criticize myself a bit, because if you look at capacitors, if you look at a breakdown of the power, we are sitting at 40% losses in the capacitor, which I think is a little bit too much. So we could have improved it, but the reality was, like, I was sitting with experimental capacitor boards, so we could have pushed 92 to probably 93 or something like this, So there was room for improvement in capacitors for sure in their losses. But of course, you will see that you will have losses in aluminium, copper, as well as in ferrites among the magnetics, where you can try to improve some, but some you certainly will have. Okay, so with that, I think I will stop with the demonstration of IPT systems and go into more of cutting edge inductive power transfer systems, So we talked of electric vehicle applications, and there we introduced the idea of multi-coil topologies. But there are other application examples. So to give you an example, we look at modern office spaces. In modern office spaces where we have meetings in the meeting room, we already have dongles which can actually move on between, let's say, one laptop to another for each of the presenters to have, let's say, easy mode of presentation rather than actually bringing a wired connector between each laptops, So we already went the wireless way, if you want, for data. Now the question is, if you have 10 people in the same meeting room, each of whom have smart devices like laptops and mobile phones, can the office furniture in itself become wirelessly charged? Can the office furniture have multi-coil topologies that can actually charge your laptops without you having to plug each of those laptops into a power pin? So that's happening. That's one place where multi-coil is also being applied. The next is, for example, high power application, which is another end of the spectrum. When you're looking at electric vehicle buses, 500 kilowatt charging, there we are looking at multi-phase topologies. So you have, for example, the three-phase power lines in the AC. Similarly, we produce three-phase 85 kilohertz power lines, each of which then are in the form of a track or a loop. So these are rectangular loops which are long, which actually then transport quite a lot of currents, which creates magnetic field enough to transport power to the bus in itself. So this is another place where we use multi-coil, in this case specifically multi-phase, let's say, IPT systems. But be aware of one thing, like, there is a phase A, B, and I show it as C written here. You should be careful on that, because when you take three phasors and all the phasors are separated by 120 degree, the resultant is always a 0. You don't produce any magnetic field. So if you want to have a strong magnetic field with three-phase system, you better transpose one of your phases, otherwise your let's say, phasor sum will add to 0. So it's on purpose that you have an accent above the C there, right? Okay, so what is a problem with multi-coil IPT topology? So we looked at the benefits about, like, about the tolerance to misalignment that it has, but there are other issues that come with multi-coil topologies, for example. So imagine that you have a primary system with two coils, and you have secondary system with two coils or two pads, right? We want power to flow from the primary to the secondary. So this, let's say, vertical power transfer is what is intended. The same here as well. But in reality, we have mutual inductances between every coil to every other coil. In communication engineering, this is called crosstalk. So we have crosstalk. The problem is when you have this parasitic coupling between two coils of the primary, we essentially can transfer power from this primary to this primary, because both are tuned systems. As far as this coil is concerned and the physics is concerned, it doesn't care your secondary is here or if this is, because for it, it's a tuned system. It just produces magnetic fields, and the physics means that you also transport power to the other primary pad, which is unintended. So solving this has been an important challenge that people have thought about. So let's look at what kind of problems are we facing. So when you have two coils which are tuned to the same frequency, which are essentially primary, but then what happens, so we find it difficult to independently operate the two coils. That's simply because of this parasitic coupling. It can detune the system. Just because you have a neighboring coil in the primary that's also tuned to the same frequency, you can actually detune this coil sometimes, and it of course causes undesired power flow. I want my power to flow to a secondary, but now I'm transferring some amount of power to this coil as well, So how shall we solve that problem? So I give credit to the University of Auckland. They had a study, for example, in the DD pad, wherein if you actually displace one pad on top of the other, there is a point of displacement between the two pads at which actually the coupling between these two coils reduces to zero. So if you can actually displace the two pads on top of each other at this coupling, null coupling point as we call it, then you don't have unintended power flow and no detuning effects as such, But the problem is because you have now overlapped the two coils, the range of this pad relative to the DD pad has now reduced, because in the DD pad, you could have pushed power to much higher misalignments, but now you're restricted by that. Another solution that also one sees with multi-coil topologies for EV applications specifically is double D quadrature coils. So as I had mentioned, in the normal segmented coils, we have currents flowing in two different directions, one in clockwise, the other one in counterclockwise. So it produces a largely horizontal flux at the center. So if you're a point at exactly center of the coil, most of your flux is horizontal. This quadrature coil is put in such a way, it's a normal circular coil or a rectangular coil for that matter. Any normal single coil will actually have a vertical flux at the center point, so these two are orthogonal to each other. And therefore, by adding this orthogonal coil or a quadrature coil, what could happen is we can actually create, first of all, there's an additional coil to transport more power, so we can transport more power. And second of all, there are certain alignments at which, the quadrature coil can also push in additional power, which you wouldn't get with the normal DD coil. So this is another solution to null coupling and to misalignment problems, which multi-coil topologies have, But of course, thinking really out of the box, not many groups have worked on another idea, which is multi-frequency IPT. So we started at TU Delft working on this, I think in 2013-14 timeframe. The idea of such a system is basically from or the inspiration is a little bit from wireless communication, for example. So if you imagine your room right now, you are impinged by electromagnetic fields at different frequencies. You have no clue about it, So if you, for example, turn on your radio station, you can tune to 96.5 FM. But by changing the knob, which essentially changes a capacitance of the tune system, you can actually tune it to another radio station, So you can tune to multiple radio stations which don't interfere with each other. Why don't they interfere with each other? Because you have created a resonant network that actually only accepts the frequency that you want. So this is the inspiration for us. If we can actually change frequency, and if you can design a compensation network that only accepts the frequency that you want, then the crosstalk is not a problem at all, or you can eliminate lots of issues of crosstalk, isn't it? So another way to decouple coils is using different frequencies. So one other work, for example, from Professor Lukic, that time in 2014, what he did is he ended up building let's say a inverter that actually generates first harmonic and the third harmonic. So this is 85 kilohertz, this is 255 kilohertz, And the idea was you complicate the resonant topology here. So as you can see, it's a ladder LC network. So what is so unique about a ladder LC network is that it has a characteristic equation that has a higher order. So you have 1, 2, 3, 4 energy storage elements, So your network has multiple number of poles and zeros. So by doing that, what you can do is you can essentially make a circuit that can actually accept both your first and the third harmonic, because you can create two poles, and the location of that poles is dictated by the inductances and the capacitance value of this design. So therefore, you can have a more complicated, let's say, a resonant capacitor tuned network, which can actually accept multiple frequencies. you push both the frequency through the primary, you get both of them at the secondary, have similarly such an acceptance circuit here, which can then power, for example, through a rectifier, a load, So that's an interesting way to solve this multi-frequency problem. You can also have, for example, DD structures with both the Ds operated at different frequency. This is the ambition, or this is the vision that we took in TU Delft. And I'll explain a bit about some of our results with that. So if you're looking at series resonant topologies, all of which are tuned to 4 different frequencies, 20 kilohertz, 50, 100, and 150, for example. A series resonant network pushes the overall impedance to a minima at the resonant point. I think this is very clear from fundamental physics. But what is interesting to note is also that at post-resonant frequencies, at frequencies more than the resonant frequency, the circuit behaves more inductively. You see, so you have a very, let's say, linear variation in the logarithmic scale, So that's because the circuit has become omega L dominated, for example. But when you have pre-resonant frequencies, the circuit is highly capacitive. It's dominated by 1 by omega C term, So when you have 2 different frequencies, for example, 20 kilohertz and 100 kilohertz, the green and the blue, for the 100 kilohertz system, the 20 kilohertz system is lying in its capacitive dominated region. And for the vice versa, it is in the inductive region, So the attenuation, therefore, for the other frequency component depends if it is a higher frequency or if it is a lower frequency, and that attenuation can be more capacitive or can be more inductive. So that's something to understand and think about. So we did finite element simulations with COMSOL again with this kind of a problem, imposing 20 kilohertz and imposing 100 kilohertz. What we realized is, okay, with the 20 kilohertz system, if both 20 kilohertz and 100 kilohertz magnetic fields are present in the system, with a well-tuned system, we receive mostly the 20 kilohertz component, but we do receive not a slight amount of, let's say, 100 kilohertz component, and the vice versa. The blip is much smaller, but this blip, the size of this blip depends on the quality factor, So you can tune the quality factor of the system to further reject this out. But my main message essentially is that we are receiving, even though the space around is impinged by both the frequencies, we only receive what we have tuned the system for. So that way we can eliminate crosstalk. So I did some experiments with my student, and this was for a very simple demonstration. We charged some mobile phones that time. So with 2 systems, 100 kilohertz and 20 kilohertz. So these pancake coils are basically the transmitter for the 2 frequencies and the receiver. What was even interesting was we did the worst experiment, which was to put the 100 and the 20 kilohertz on top of each other, and the same with the receiver, and yet we could see that, okay, this is the 100 kilohertz component, this is the 20 kilohertz. You do see some harmonic in the waveform, but largely we only transport what is the tuned frequency for the system, So even under the worst case. Okay, now I will speak a little bit about wireless transfer, power transfer, specifically for drones. Why drones? I mean, in this situation of the pandemic, one is seeing that drones are becoming more and more important. So whether it be for supplying medical equipment, or whether it be for delivering, let's say, medicines at a rural background, or even for medical health checkups, if you want to transport some blood samples and so on, and because the place is so rural and you want to have some form of communication, drones is one method by which you could actually deliver these essential equipments even under the conditions of pandemic, and of course drones are being increasingly used for surveillance. Now look at a vision for this. So the idea is, like, in the future, let's say more and more drones are being used for all kinds of these purposes, and you are in a warehouse with a lot of medical supplies, let's say, and we are dealing with, I don't know, a swarm of 200 or 500 drones. Charging each one of them physically or by means of conductive charging is going to be a challenge in itself, you know. On the other hand, if you have these wireless charging plates or pads where the drone can actually sit and charge by itself, you have a very elegant solution that can make an autonomous charging system for drones, you know. So that was the inspiration for doing this. So I defined a BSc project for one of my students in U Twente. It's a bachelor project. So we were looking, there are not many groups in the world that are dealing with wireless charging in drones. Some of them are at, have researched it to quite a degree, but not many are doing it. So essentially, this is a different regime from what we are used to with electric vehicles, you know. So we are looking at lower power levels, typically less than 1 kilowatt. So for example, most often 75 watts, 100 watts, 150 watt drones, you know, it depends on the type and size and the application that the drone is doing. So for these kind of application, we don't want to sit with inverter with multiple switches, you know, so we want to have as minimum switch as possible. So when you look at switch mode power supplies, because you are also interested in efficiency, you don't want a linear amplifier. You are looking at, for example, topologies where there is very few switches, but which are resonant, let's say, topologies, you know. So we get 0 voltage switching, 0 current switching and all that. So for that, one of the good examples of a switch mode power supply is class E amplifier. It has one active device. So this could be, for example, a silicon MOSFET. It could be a silicon carbide MOSFET, for example. So we trigger the gate to turn on and turn off like a switch mode power supply. We have a DC inductor and a snubber capacitor. And normally the class E amplifier has a load here because it's used as an amplifier to drive something to the load. But now what we did is we tweaked the resonant part of the class E amplifier, the capacitor and the inductor. This inductor is essentially the base pad now, you know, and we couple it to another secondary inductor in the drone below the chassis of the drone, for example, with the resonant tank there, and transport the power to the battery bank. So we have started working on drones. We will be, because of Corona, we couldn't unfortunately build a big system. We will be doing it in time, but it's an important application, something that Amrita can also pick up, for example. Another thing that is interesting is to look at market. Where do we see potential applications of inductive power transfer, you know? So I told you, like, it's a mature technology where you're looking at microwatts all the way to hundreds of kilowatts. So this picture should give you, like, you know, a good example. So microwatt, where does it come in, for example? So you can imagine pacemaker. Pacemaker is very important for people that have heart problems, isn't it? We don't want to operate upon a patient every time that you want to change the battery of the pacemaker, for example, you know. So that's a very good application where wireless charging can come in. But the problem is it is highly safety oriented. So we have to be very careful with the fields. But hey, at microwatts of power, safety can be guaranteed, you know, so we could still do it. So for biomedical applications, we are looking at microwatts to a few watts probably. We can also, of course, have wireless charging for all kinds of electronic equipments, including laptops, iPhones, iPads, and so on. We also can have, for example, kitchen equipments that can be made wirelessly charged. A quick and good example that I can remember is when I used to help my mother with making a chutney out of the mixer grinder. If you had a wet hand and if you were to turn off your switch, there could be instances where you could get a shock, isn't it? So I have had that electrocution myself. So why not have a pad on in the kitchen by which, you know, we transport power by magnetic fields, and you don't need to plug in anything into, even with your wet hands, you know, for example. So all kinds of home appliances can be made into wirelessly charged devices. What is interesting from mobility's point of view is these. So we can have e-scooters and e-bicycles and rollators and, like, you know, electric vehicles and even buses. So we really are looking then at applications in the multi-kilowatt range for electric mobility specifically, and for, let's say, home appliances, it's in the 500 watt to a kilowatt range sort of. So this is how power and applications, the flurry of applications that you can imagine with inductive power transfer. Now, next, I would focus on Qualcomm Halo, which was a company I worked for from 2016. So we were pioneers in wireless charging for electric vehicles. So we developed base pads, vehicle pads, the electronics. We were basically an advanced R&D division that were making reference design. We never had a let's say industrial rollout or whatsoever. So we engaged into licensing agreements with tier ones, which then manufacture these in large volumes, like the Bosch and Continentals and so on. So in an industrial implementation, we have the power supply. Sometimes it's called a wall box. So it takes the AC grid, like I showed you, and it has those series of converters, like, you have the boost converter. It's called a boost PFC, a power factor regulator, power factor PFC, followed by an inverter, followed by a capacitor, bank, for the resonance. So all of them are present in this box. And then you have the pad at the floor. You have a pad below the chassis of the car. You have active electronics here, which actually condition the power into DC, which then can pass over to the battery. So this is how the industrial implementation looks like. We were working at 3.3 kilowatt, 6.6 kilowatt, 11 kilowatt, all the way up to 20 kilowatt. So these are SAE standards for charging electric vehicles, basically. If you look at wireless charging as a problem, there are multiple other issues other than power transfer. So you have magnetics, you have power electronics, but you also need ancillaries, as we call it. So what are the ancillaries for? For example, if you have, just like aluminium shield explanation, if you have, for example, metallic coin which is placed on the pad when the pad is transporting power, the metal in the presence of alternating field creates heat. So, the metallic coin can get hot. It can potentially scorch. It can create fire, and that is a safety hazard. So we need to be able to detect foreign objects, especially metallic objects, and either have the system cut out the power or have a user throw away the metallic object, by giving an indication to the driver, for example. In case of, for example, a cat which is then rolling close to the pad, the presence of high field strengths in the vicinity of the pad is going to create health issues for the cat as well. For that matter, even a child, So we need to detect the presence of moving objects, for example, cats and human beings and so on, which are in the vicinity of the pad, which can be unhealthy for them, and actually take actions based on that, So these are the let's say ancillaries of the system, the foreign object detection and living object protection. We also need to develop software and communication, because essentially the dream is like you park the car in a parking bay, you go to your office, and then you have your mobile phone which then presses the button like start charging and the car charges, So it's a comfort sort of scenario in the future. We also need system integration, you need regulatory compliance, EMC, and so on. So the field in itself is penetrated by different fields, different disciplines, power electronics, magnetics, EMC, control, FOD, LOP, and so on. So it's a very interesting multidisciplinary problem. In our Qualcomm Halo global team, when I was still working, our engineering office was headquartered in Munich. We had engineering offices in Switzerland. We also had one in Auckland. The headquarters of Qualcomm is in San Diego, California. What was interesting is among all our workforces, we had about 30% of total staff that were PhDs, So we were quite research intensive. If you look at, for example, the engineering offices in itself, the number is even more higher. So we were several PhDs, all of which wanted to look at different solutions and make patents and make new reference designs and so on. Another development or another trend that we are seeing is the concept of autonomous driving. So when we drive a normal car, the presence of the human factor brings in our senses into the car. For example, our eyes, our ears, our brain, and so on. So when we replace the human being and when we look at a driverless car, we are looking at a lot of sensors that the car has to sit with, So we are looking at the eyes, for example, cameras, radars, lidars. So all these sensors detect the environment, detect things around in the vicinity of the car. and the brain is replaced by the GPU, the general processing unit. Each of the sensors can also have distributed, let's say, processing as well. So there are different architectures for the same. But as we move over from different levels of autonomous driving, so we have level 1 all the way up to level 5. So level 1 is where maybe one of the system is automated, and with level 2, we have multiple systems that are being automated. So this is called ADAS. ADAS is where you have advanced driver assistance system. So it's not really pure autonomous, but many operations are being automated, So for example, adaptive cruise control, lane departure warning system. So there are lots and lots of features that cars get as we add more and more levels of autonomy to it. So the main message is autonomous charging can be a feature of autonomous driving. It is not yet a feature of autonomous driving because it only impacts driving, to be honest. With autonomous charging, maybe wireless charging can also become part of the vision of autonomous cars. But there can be competing technologies. For example, we work a lot with wireless charging by inductive or magnetic fields. Tesla, for example, works with a movable robotic arm that can actually charge the car. So that's also an autonomous charging if you want. But so you have multiple solutions. They have their own advantages and disadvantages, and maybe one of these will win. But to make the experience of autonomous driving complete, obviously autonomous charging should be part of autonomous driving as well. Okay, now we talked of patents and maybe something to for the students or for researchers to further work on. I decided to, one of my impact in Qualcomm was to also come up with solutions for harmonics, the problem of harmonics. So, for example, when you have a bridge, an inverter bridge, because it's at 85 kilohertz, we can't do sinusoidal pulse width modulation. So we are looking at square wave voltages. Like every student of mathematics knows, square wave is an odd function. So you have a very nice fundamental, but you also have the third, the fifth, the seventh, the 11th. So you have all kinds of odd harmonics sitting in the inverter. Even though the compensation network creates attenuation for these higher frequencies, but we still have milliamperes of current that are flowing through some of these harmonics, which actually can then interfere with other existing uses of the electromagnetic spectrum. For example, long range amplitude modulation, long range AM stations start like, somewhere in the 500 kilohertz, which actually would match with the 7th or the 11th harmonic. Therefore, we have very stringent, let's say, guidelines as to what should be the levels. In some case, the noise floor is the level that we have to meet, So the H field limits are very restrictive, especially for the higher order harmonics. So for 85 kilohertz, the limit is sitting at 82.5 dB microamp per meter. But with increasing frequencies, it becomes even more restrictive. So one of the solutions that I did was to use, for example, the cable in itself as a filter. You can actually read this patent later. It's called electrical feed line integrating filter. It is no longer assigned to Qualcomm. It's in fact assigned to Vitricity because Vitricity took over all of Qualcomm's patents because Qualcomm decided to exit the scene of wireless charging. So Vitricity is basically a Massachusetts-based startup. It's an MIT startup which is now continuing to work on EV-based wireless charging system as well. Okay, so after this long presentation, I think it's time for me to give my concluding arguments. Energy engineering or power engineering, a very interesting discipline of engineering. So we deal with new and renewable energy generation. We also deal with distribution supply and also, for example, novel applications of renewable energy like, electric vehicles and so on. So as I said, for example, wireless charging is a very high-tech technology. It increases comfort, but at the same time, in the current environment, we must make no compromise with sustainability. Transportation, I would say, has been a very lazy sector when it comes to shifting to electric, even though electric cars have a very, very long history. So if we can electrify EVs, we are sitting at 23% reduction of carbon dioxide emissions. In the current climate of global warming and climate change, I think transportation becoming electric is an important part of the puzzle. So we will have more and more e-bikes, e-scooters, EVs. So for example, in India, e-scooters is scooters are generally popular. So the market for e-scooters is going to be drastic. So doing charging in any form, whether it be wireless or wired, is of course interesting for e-scooters as well, you know. In most countries, the biggest pitfall to acceptance of electric vehicles is the charging infrastructure. So I must say we don't have enough conductive charging as well as inductive charging. Inductive charging maybe even less, but conductive charging definitely we need, because we need to augment the infrastructure to be able to shift from like fossil fuel based cars to electric vehicles. Lot of let's say side disciplines also emerge. For example, batteries are becoming very, very important. In 2010, the cost of the battery was about 50% of the cost of the electric vehicle, you know. Now with more and more the scale, let's say the law of economics, the economics of volume is now dictating costs. So the price is reducing. So at one point they were saying in 2020, maybe battery packs can reach $100 per kilowatt hour. I don't know. I cannot foresee it coming, but it is becoming cheaper therefore, you know. So battery and cells are very important. Even at that rate, it probably costs 1/3 of the cost of the car is then with the batteries, you know. So battery and battery management system will become important. As we switch at much higher frequencies, we are employing more wide band gap semiconductors, so newer switches that can switch higher powers with higher frequency as well. We also foresee that all of the switching at higher powers at higher frequency will create more and more interferences, more and more noise sources. So EMC issues is also being foreseen. So it fits very well that we are in a group that combines different disciplines, you know, power electronics, EMC, control, and so on. Yeah, I mean, with this, I think I will conclude the webinar and open myself for questions from the audience.
So we had a fantastic interaction. Prasanth, how was the experience?
It was great. I mean, thank you everybody for inviting me, and I mean, also the Q&A, some of the questions were quite interesting as well, some from which I have to think as well, you know. So great. I mean, I hope that some students can actually further work on related topics to what was described here, and let's see.
That's great, Prasanth. It was a wonderful time having you here with us, and we really hope to keep this connection going, you know. And thanks a lot for being here.
Thank you. Yeah.